Okay, so we talked about rotation in three-dimension last time, and today we are going to learn about, today and in the subsequent two classes, we are going to learn about rotation in three dimensions. This is the symmetry of any physical system. Any Hamiltonian with central potential, that is Hamiltonian has the form H is equal to E square by 2m plus B, which is the function of the modulus of the radial component. And since both the vector P and R appear only in terms of their magnitude, this Hamiltonian is invariant under rotation. Since the magnitude of P and R after a rotation remains the same, this is the symmetry of the Hamiltonian, which means that some configurations of the system it will have this symmetry, some configurations which will not have this symmetry, but there are definite properties of all the configurations that follows from this symmetry, and that is what we are going to learn today. So I will tell you how to catalog rotation, that is how we should label different rotations. So it's clear that rotation in three dimension, it's clear that it forms a group, which is a continuous group. And it's parameterized by, labeled by, a group element is labeled by some number of parameters. So how many parameters do we need? That is the question that we will first find out. We will not be able to see that part of the body. So we have to find out how many parameters we need to label a group element, and given a group element we need to find out how it is related to other group elements and stuff like that. And since it's a continuous group, what we have learned is that corresponding to each of these group elements, corresponding to each of these parameters, the independent parameters, each independent parameter, we can associate a generator of infinitesimal function. So far, it's everything follows exactly what we have seen in terms of other continuous groups, like the group of translation or the group of rotation in three dimensions. Except that in those cases there was only one parameter. Group of translation in three dimensions has three parameters, but there is a crucial difference in this case is that this group is non-commutative. That is to say that if you have a rotation 1 followed by a rotation 2 followed by rotation 1, this is not rotation 2, rotation 1 followed by rotation 2 in general. Although there may be specific examples where this happens, in general this is not true. And we have seen one demonstration of this way, right? So this group is in general not commutative, and actually most, generally any group commutativity is not a required property of a group, so that's an additional property So we don't expect that new element should have to be commutative. So we want to now learn how to label these parameters. For that we need to know how many independent rotations are needed to characterize a rotation. That is the question. And the answer comes from classical mechanics. Since we are discussing rotation in 3D, answer comes from here in classical mechanics, which is Euler's theorem for rigid body mechanics. We studied rigid bodies in classical mechanics in MSc here. Was there time for that? Did you study rigid bodies? I don't get a clear answer.
Yes, sir.
Yes. You are saying no. Yes. Did you study Euler's theorem? Yes. What is Euler's theorem? Is Euler's theorem? Euler's theorem seems to be something you learned. Raise your voice. You have a cold. You don't have to give up. Someone else can give up. Yes, Gaurav. Euler's theorem. Huh? Euler's angle is not Euler's theorem. Euler's theorem?
Any translation would say eigenvalue is 1, it is a equation.
What?
For rotational translation, eigenvalue of the beta either 1 or they more than 1. Statement like don't know the type of data.
Okay. Euler's theorem? Not correct crossing. Not Babu. Manish. Manish. Sarva. You. Engineering. You do Euler's theorem. So anyway, there may be more versions of Euler's theorem. Probably the most famous Euler's theorem is e to the power I pi is equal to minus 1. I am not talking about that. We are talking about Euler's theorem for rigid bodies. What is a rigid body? What is a rigid body? क्या नीचे होगा? बॉडी का फिक्स रहता है तो मूव करेगा कैसे? rigid body can move, right? Any motion instrument fixed. That's a contradictory statement, right? Motion means something not fixed. Interparticle or interparticle separation remains fixed, right? By the way, this is impossible in quantum mechanics, also impossible in physics. So it's a very ideal classical concept. Anyway, so what does Euler's theorem say? Euler's theorem of rigid bodies about rotation in 3 dimensions. It says that if a rigid body moves in such a way that one point remains fixed, not arbitrary motion, which means translation is ruled out. You have to have one point fixed. Then what happens? Can someone tell me now? It will be rotation only. No, there is nothing to do. It's not dynamics. Momentum inertia is not involved. If one point remains fixed, then
The same center of mass.
Then?
Same center of mass.
same
Of the center of mass. The center of mass.
center of mass. Any arbitrary point, it doesn't have to be center of mass. Any arbitrary point remains fixed, then not only that point, the whole axis will remain fixed. Which means, first of all, it cannot be a translation because in translation, क्या check करना है? So, what we are saying is that a body, rigid body, if it's translation, then all points will move, right? Because all points move by the same amount. So no point is remaining fixed. So that case is ruled out. So it's a case of pure rotation. As Gurpreet was saying, that a rigid body motion, there are only two possibilities: translation and rotation. So this first assumption rules out translation. The second assumption, therefore it has to be a rotation. The second statement says that in a rotation, if you fix one point, that is of course the point is fixed, if you in a rotation, a whole axis remains fixed. Which means you can characterize the rotation by an axis, okay, along which the points do not move. All points along that axis remain fixed. What moves is a rotation around that axis. So, and write it in your own words. In Euler's theorem, if you in a rigid body, if one point remains fixed, then a whole axis remains fixed. It's a rotation, and that rotation is characterized by the direction, which is the axis, and an angle by which the rotation is, the amount of rotation. That tells you therefore that what you need is a direction, actually more precisely is just an axis, and an angle. So the direction of the axis is the axis of rotation, around which the rotation is being made, and an angle, which is the amount of the angle of rotation by which it is rotated. So let us characterize an axis by a unit vector, because it's the magnitude is not important, it's the direction which is important. So L is the unit vector, and an angle which is say alpha. So that is how we should characterize the rotation. But we don't even need an axis. What we need is one line, because the line remains fixed, right? So it doesn't have a direction. This direction and this direction are equally good. But we want to specify a direction because then that helps us to tell in which way we are rotating. We take rotation in the counterclockwise direction, anti-clockwise direction as positive angles. In the opposite direction, we treat them as negative angles, and for that we need to specify the direction. Otherwise, Euler's theorem only requires a line to be fixed. Okay. So we need a direction and a line. So what does rotation do? Given the vector x, y, z, or this vector x, after rotation you get a new vector x prime, which is given by x prime. This is given by a rotation. Since this is a matrix, I can write the rotation as a 3x3 matrix. Right? And since it is given by an angle and a direction, I will write this as Rn alpha is a 3x3 matrix. Okay? So this 3x3 matrix has three parameters. What are the three parameters? N requires two parameters, theta and phi, and alpha is one parameter. So that's two angles and one angle. So altogether, three angles. What are the ranges? N is the unit vector. So we can take it as a point on the unit sphere, right? Since it's a unit vector, we can take this to be a point on the unit sphere. Point on the unit sphere is given by two coordinates, theta and phi. So theta and phi, theta goes from 0 to phi, phi goes from 0 to 2 pi, of course these 2 points being identified, and alpha is an angle, and we have to specify how alpha behaves. This, can you tell me what will be the values of alpha? Of course, alpha is to start from 0, but whether it goes from 0 to 2 pi or 0 to pi. Or pi by 2, pi by 2, what should it be? 0 to 2 pi. 0 to 2 pi says Shiva. Who else agrees with me? Anybody has a different opinion? 2 pi. 2 pi. Everybody is for 2 pi. I by 2. कम करना है तो बहुत ही कम करें. Why pi by 2 and why 2 pi? 2 pi is okay, natural. I understand the condition by 2 pi comes back to this, right? You said pi. Why pi?
Completing the rotation energy.
Yes, completing the rotation happens when we rotate by 2 pi. Right?
So if we will go from 0 to 2 pi will complete, and if we go from 0 to pi only, so this rotation will complete. So 0 to pi,
And it's not this rotation, I'm talking about only one rotation. All possible rotations have to be captured. So I don't understand your explanation. What are you trying to say? I have a body like this, okay? And I want to see what all possible rotation this is possible. Is you need what all values of alpha, beta, and phi you need to specify all possible rotation of this box. All possible rotation. So first I specify a direction of rotation and then I specify an angle of rotation. So direction is given by theta and phi, which are from 0 to pi and 0 to 2 pi, because those are points of the unit sphere. So after that, given this direction, this is alpha. So what are the allowed values of alpha I need to characterize all possible rotations? So Shivam said 0 to 2 pi because this comes back to this. And Sneha, right? Sneha is trying to say 0 to pi. Gurpreet said 0 to pi by 2. That's the wrong answer. 2 pi is also wrong answer. Pi is the correct answer, but I want to know why. Yes.
So direction of n cap reverses.
That point is fixed. That axis is also fixed. You said.
For one particular rotation, axis and angle are both fixed.
Then if you will rotate by 2 pi, it will complete rotate
Yes,
the theta, so it will be twice of that. It will
Twice of what?
How to explain that? Like,
How to explain? Clear?
no. If you rotate any object with a fixed axis and you are going through 2 pi, then it will rotate twice now. Axis
No,
is
it will
fixed.
not rotate twice. It will rotate only once. Axis is fixed. That axis is fixed, right? If you want to describe all the rotations, you have to take 2 pi. Because otherwise you will have half the rotation. So your argument is not right. Yes, somebody was trying to say about the axis. Who was saying? Rahul, you were saying? You were saying? Who was saying? See, we have also directions n. N are all points on the unit sphere. All the directions. So each point is the direction, right? In particular, if you take a direction here, you also have minus n. Both are included. N here, this is minus n. Right? So if I rotate by n, that's also rotation about minus n with an angle which is what? negative of that, but there is no real negative angle. This is
Same.
actually
Same.
one minus that angle, right? So, since we are counting on n, we have to count only rotation by pi, because rotation by any angle which is more than pi is a rotation by an angle which is less than pi. You see that? Talking about arbitrary direction, take z direction. Rotation about z direction by an angle alpha is the same as rotation about the direction minus z by an angle 2 pi minus r. Right? So once you start from 0 and reach pi, you have covered 0 to pi here around plus n, and around minus n you have covered
Pi to 2 pi. Pi to 2 pi, sir.
2 pi minus
Pi to 2 pi.
right? So if you take all the directions, you only have to restrict to pi. Otherwise it will be double counting. In fact, there is a double counting here also, because the rotation by pi is included in both. Rotation by pi about n is the same as rotation by pi about minus n. So these two rotations are actually identical rotations. This rotation is no rotation at all. That's not so much of a problem. But these two rotations are non-trivial rotations and they are identical. That's why characteristic rotation is a bit tricky, and we'll come back to this point later. Remember that there is an ambiguity. We are actually counting almost all rotations we counted only once. But rotation by pi for any direction we have counted twice. So we have to come back to this. So how do we, okay, maybe this is the best place to do this. How do we, what is the geometrical space of rotation? Let's go back to rotation in 2 dimension first and see what we got there. That case is much simpler. Not any of these complications don't arise there. It's also commutative. So rotation in 2 dimension, as we already studied, is x, y, also sin y prime. It's the 2 by 2 matrix, and then it's y. The 2 by 2 matrix was given by cos alpha minus sin alpha, cos alpha. Okay? And alpha was an angle which took values on the circle. Alpha starts from here and it takes value from 0 to 2 pi, and the points 0 and 2 pi are identified. So this is one complication, that these 2 points are identified, but otherwise geometrical space is a circle. Okay? So the geometrical space that characterizes rotation in 3 dimension is a circle. Okay? What is the geometrical space that characterizes rotation in translation in 1 dimension? Yes? Line. It is a line. This is a circle. That's the difference. Okay, what about the geometrical space here? That characterizes the rotation. Sorry? Sphere. No, it's not a sphere. So we have to find. It's actually not straightforward. So let me try to explain that. N, as we agreed, are points on the surface of a unit sphere. So this is unit sphere. And we have arbitrary point here, which is given by how much you move from the z direction and what is this plane which is away from this x y z axis by this is r. So this is the point which is theta. This is arbitrary. We could have said that we don't take all points on the unit sphere, but we start by taking all points on the unit sphere. Right? So that is what we are taking. So this is the first 2 angles parameters. We get points on the 2-dimensional sphere. Is this part clear? So we have to put the extra information about the angle. The value of the angle is what? 0 to pi. So we can agree that we'll take a solid ball of radius pi. Okay. So now we are not only talking about the surface of the sphere, but we are talking about all points inside the sphere. Any point on the sphere, and any point on the sphere, meaning if you move along the line, the direction does not change, right? But if we move along the line, we are changing the angle of rotation. So you take alpha to be the radius, the radial distance inside the ball will characterize by alpha, the amount of rotation. So the surface of the sphere is just the theta point. Interior of the sphere, that's the radial direction, we take to be alpha. So if we take any point inside the ball, we have three coordinates, right? The radial direction alpha, which tells me what is the amount of rotation, and the direction theta phi, which tells me the angle of rotation. This way we can characterize the rotation completely. Do you agree with this? This is clear. Okay. So the radial distance in the geometric space is the interior, not just the interior, the unit ball of radius alpha, radius pi. This is the geometrical space. So any point has theta phi and alpha. So I should write alpha theta phi. This is the radial coordinate, and these are the usual angular coordinates. So this corresponds to n, and this corresponds to the angle of rotation. Is this clear? I need to put information about three angles. This radial distance doesn't look like an angle, but that doesn't matter. The value is from 0 to pi. That's all we need. So, what is the objective? The objective is that given any rotation, you should be able to give me one point inside in this geometrical space, and given any point in this geometrical space, I should be able to find the rotation. Are these two conditions satisfied or not? That's the question. So given any rotation, I have direction n, so I have theta and phi. So I find theta and phi on the sphere, let's say, and alpha, which tells me how far from the origin I am. So I choose a point depending on the value of phi. So I find one point in the geometrical space. Conversely, given this point in the geometrical space, I first find what is the direction, that is from the origin which way I am pointing, that gives me n, and how far I am from the origin, that's alpha, that gives me the angle of rotation. So I have the geometrical space that corresponds to the space, all the possible rotations in 3 dimensions. Is this clear? Now, it may seem like the geometrical space is the unit ball of radius pi, but that is where the problem arises. You see that, as I said, this point and the point which is exactly opposite to this, on the other side, I take any point, join it to the origin and go to the other side when I am on the surface of the sphere. That means rotation by an amount pi. So this point corresponds to rotation by around the direction n by an amount pi. This corresponds to rotation by an angle pi, but around minus n. And as we have just discussed, these two rotations are identical. So, for the points in the interior of this unit ball, we are counting rotation, every rotation is counted only once. But when we come to the surface of the ball, that is for alpha equal to pi, we still have a problem of double counting. We avoided double counting by not taking alpha from 0 to 2 pi. We restricted it to 0 to pi, right? But that eliminated double counting for all the angles from pi to 2 pi. But we still have the problem of double counting for alpha equal to pi. Right? Is that quite clear? As I was saying that rotation about z by an angle phi is same as rotation about minus z by an angle phi. So if I am in the z direction, this point, the north pole and the south pole actually denote the same rotation. The north pole and south pole are not special. I can move this, and this point and this point are opposite to each other. They also denote the same rotation. Right? So every point on the surface of the ball of radius pi denotes the same rotation as the point, as its, there is a name for this, as its antipodal point. What is an antipodal point? Given any point, you join that point to the origin and continue until you hit the surface again. That is the antipodal point. The antipodal point of the north pole is the south. Antipodal point of Delhi is something in the southern hemisphere. On the other side, I don't know what. You can find out. Okay. So every point is an antipodal point, and these two antipodal points they denote the same rotation. Is that clear? Diametrically opposite. Right? Except that there is no diameter in this case. This is a two-dimensional sphere. So, yeah, the diametrically opposite English word, which is the technical name is antipodal. They denote the same rotation. So I should not be double counting. Right? So I should count them only once. So how do we do that? We can restrict. We can say it's very here. We can say that we'll count only the boundary points. We will not count in the lower hemisphere. We will count only on the upper hemisphere. Right? Then I am not counting this rotation and the same. I am not counting them twice. I am counting them only once. So the boundary I will consider only on the upper hemisphere and not on the lower hemisphere. The problem is gone? No. Equator is still included. If you include equator, you are counting double again. Right? If you don't include equator, you are not counting those points. So you have to count the equator. And if we count the equator, there are antipodal points here also. Right? So we have to count only half the equator. Problem is gone? Problem is gone?
Yes.
No. The equator, half the equator has two boundary points, right? So you have to count only one. So, sorry? Not quarter. I have to count the half of the hemisphere, right? The surface of the hemisphere, I have to count only half the hemisphere. Then I have equator in which I have to count only this half, and this half has 2 points, so I have to count only one of them and not the other. Looks very ugly, weird, right? There is a better description. So I can discuss a better description, but that's actually a digression. I don't know whether I should do that or not. So let's try to see what this antipodal point, what does it do in one dimension. Here, right? Here also there are diametrically opposite points. Right? I mean, it doesn't arise here. Here all the rotations are counted. There is no problem with that. But suppose I try to identify just as a geometrical problem. If I have to identify diametrically opposite points, that is antipodal points on the surface of the circle, on the surface of the boundary of this disk, which is the circle, then what do I get? Like there, instead of upper hemisphere, we will have to count the upper semicircle. Right? But the problem is not gone because this point and this point are the same. So we have to count only these points and then identify this point and that point. That becomes a circle again, right? It's from 0 to pi, and pi is same as 0, so this becomes the same. I'm not talking about rotation in 2 dimensions, I'm just talking about the geometrical problem. If I have to identify antipodal points of the circle, I'll get this, right? Geometrically, I'll get a sphere again, a circle again. So what do we get? What is really the geometrical space? This description is ugly, but what is really the geometrical space? That's the question. Right? So first, let us try to. I don't know whether I should go into that at all or not, but since I have started, let me spend 5 minutes to explain this. We have a one-dimensional sphere, which is a circle. We have a two-dimensional sphere, just the surface. What? So this equation is x square plus y square equal to r. This is x square plus or r square. The question is x square plus y square plus z square equal to r. The two-dimensional sphere. This is not something I need. I need actually this and the analog of that. This is a three-dimensional sphere, which I cannot draw. So I will not try to draw. But try to imagine a three-dimensional sphere. How will you imagine a three-dimensional sphere? We live in three dimensions. You can't imagine three dimensions. Yeah? So we'll have to go by another. So suppose I was into that one-dimensional sphere. And my situation is that I live in three-dimensional flat space. What is one-dimensional flat space? The line. Right? So I am trying to imagine a sphere being in one dimension. So I only know one-dimensional flat space. So how will I imagine it? I'll have to imagine that I go around. If I start going around, I'll come back to the same point, right? Or I can try to imagine that I have a ball, so to say, which means to say that I have in this case an interval, and I have another interval, and I'm identifying these two intervals. So this is one line. This concept is what is called the stereographic projection. So what it means is that I have this is. Maybe two dimension will be more easy to understand. So I have a point here. This point, I can have a x, y point for this. And I can have an x, y point for this by starting from the south pole, that is this point. Join this point here and then continue until I get a point here. Then I get a point here. This way I get an image for all the points except the south pole. Where is the south pole at infinity? So all the points at infinity is actually one single point south pole which I cannot see if I leave it one-dimensional line. So I need two different lines to describe that. So this same point, if I have to take another projection, I will see it as x prime, y prime. And what is the relation between these 2 points? It's the same point, right? The relation between the coordinates of these 2 points is that if I best keep it in terms of z, which is x plus iy, is that z is equal to 1 by z. Minus or plus 1 by z depending on whether you want to do the relation or not. But z is equal to 1 by z will relate these 2 points. That actually follows from Taylor relation. You can try to work it. So what we have is that this segment excluding the south pole and this segment excluding the north pole are points in common. There you can use this identification. For this segment, the point at infinity is the south pole is missing. For this segment, the point at infinity is this point, north pole is missing. But all the other points are common and that's the relation. Same thing you can do in two-dimensional sphere. Now instead of line, you have to take plane here and a plane here. And start from the south pole, point on the plane sphere. You project, you get a point here, point on the surface. X, y, right? There is x, y, nobody is saying it. It's just x and this is x prime. So this is related to x prime 1 by. Here it is the horizon. Here, so this will be a point x, y. This will be a point x prime, y prime. and you will be able to relate this by this, the relation that I gave earlier. This is something that you may remember from your school geography textbooks. I don't know if you still have this because it's the internet generation. We used to have a thing called atlas. In the atlas there are maps of different countries, different parts of the world. But typically in the beginning of the atlas or at the end of the atlas there are two pictures, two maps. One map was Earth as seen from the top of the North Sphere, North Pole, and the other the Earth as seen from the below the South Pole. So in one case you have Antarctica at the center, and then everything else distorted and stretched out depending on how far you are going, they are stretched out, right? And the other one will have the North Pole at the center and everything else around that. So obviously that will not include the South Pole, and the lower one which is Antarctica at the center, that will not include the North Pole. So these two atlas, these two maps together, they describe all the points of the sphere. You cannot use only one map. This is true for all the spheres. For the 3D sphere, you will do the same. You have a North Pole, so to say. Around the North Pole, you have not a plane, not a line, not a plane, but a three-dimensional space, right? And around the South Pole, you have another three-dimensional space, and all the points which are not North Pole or South Pole are common to both, and you have a coordinate transformation that relates. Now let us try to imagine we are in this three-dimensional sphere. North Pole is not a special point, right? Any point I could have called up with. Same here. So you can imagine that where I am standing, this is the North Pole of the three-dimensional sphere. Right? I only see flat three-dimensional space around me. But what does it mean? It means that if I go on to infinity along any direction, that point is actually one point. Right? Here it says if I go to infinity along this direction or infinity along this direction or this direction, it's the same point. Here I have infinite number of ways to go to infinity. On the plane, I think that they are distinct. But if I move on the sphere, they actually all lead to one point. Right? So all the points at infinity are actually one point when we are on the sphere. Same, you can imagine in 3 dimension. We are on, this is the origin. Where I am standing, this is the origin. So all the direction I can think of, this way, this way, this way, all directions will actually lead me to one point, and that's the point. So now, is that point clear? I'm taking much more than 9 minutes, but if this is clear, then we can try to see what is the geometrical space we have in mind. So, as I said, that we want to identify antipodal points. This gives me a sphere. I can see you very easily, so I'm not a problem. Let's try to imagine we want to identify antipodal points here. What should we do? I don't want to count double, right? So here, when we didn't want to count double, we said that we'll count only the northern hemisphere, and then we'll identify the boundary. So here we do the same thing. We don't want to count double. We want to identify important points. We don't want to count double. So we take, this is just the surface of the sphere, not like that. We take only the points on the upper hemisphere. We still have point of double counting because the equator is excluded. We take only half the equator, and in half the equator we include only one boundary. That would be the space that we will get by identifying antipodal points. Let's try to do the same thing in 3 dimensions. Okay? What do? We have to identify antipodal points of 3 dimensional sphere. What do? We take only the northern hemisphere. What is the northern hemisphere for a 3-dimensional sphere? Starting from the origin, it's a ball of radius. Let's make the radius of the circle is not specified, whatever it is. The ball which will take me up to the equator. Right? The sphere is made up of 2 hemispheres. The 3-dimensional sphere is made up of 2. What is the hemisphere? It's a disc. This hemisphere is a line, right? Interval. This hemisphere is a disc. What is the hemisphere here? radius up to some point. 1, whatever is the radius. If I take infinite sphere, radius 1. All points in the infinite. Okay? So I will, to count only once, because I am identifying antipodal points, I take half the space. So half the space is this ball. But I still have double counting, because the points on the surface of the ball are counted twice. So I have to count only the upper hemisphere, which is this part. On that I still have the double counting on the equator, and on that I have the boundary points of the equator. So I have to take the ball, unit ball, count only the half the boundary of the unit ball, which is the upper hemisphere, count the equator, only half the equator, and half the equator that has two boundary points, I count only once. That's what precisely what we did here, right? So this space is equivalent to taking a three-dimensional sphere and identifying antipodal points. So geometrically, this is nothing but a 3D sphere with the antipodal points identified. This rather seemingly ugly configuration has somewhat better description, because a 3D sphere is a much better space, right? You are not putting any conditions. On the 3D sphere, you just say that I identify antipodal points. Then I get exactly the same space that came from. That's the space of rotation. And the 3D sphere with the antipodal points identified is the same space as this. If we don't identify the antipodal points, then I have a much simpler space, which is the 3D sphere, and that will also appear in the context of rotation, in particular in quantum. So, although it's not strictly important, it's better to keep this in mind when we discuss the effect of rotation in quantum particular point. Or a particular point where? Surface of what? This case. Yes.
So for that particular point, is there unique antipodal point?
Yes.
If you are talking about, let's say, diameter, along the diameter. So
Not along the diameter. Given the point, you join it to the origin and continue. Then you will hit the boundary only once here. This surface of the sphere is given by x square plus z square plus x square plus y square plus z square equal to pi square. Right? So if I take any point, when I join it to the origin, I get it only once. That is geometrically quite clear, right?
if you think about it, say diameter, so 8 points of first side
diameter, diameter, एक पॉइंट से कैसे बहुत सारे diameter है?
यहाँ से ये सेंटर से क्रॉस किया तो diameter हो
वही एक ही है और क्या? Any point can be uniquely joined to the center, right? You cannot join in any more than one. Okay, so any question about this? You have to imagine a pyramid and think about it a little. Any question about this? You may have heard this statement that in rotation about 2 pi is the same as no rotation at all, right? But you may have heard that in quantum mechanics this is not true. Rotation about 2 pi is not no rotation at all. It's rotation about 4 pi which is no rotation. Have you come across this statement? Huh? From me? That's right. From anywhere else independently. For fermions, you have not heard this. You have not heard this. What fermions in modern physics is something nobody mentioned this. That fermions have this property that if you rotate by 2 pi, the configuration doesn't come back to itself. It comes back to itself up to a sign. Then it becomes minus the same configuration. Then you have to do another rotation by 2 pi to come back to the same state. And that is related to this fact that we are identifying antipodal points. So we'll come back to this. Any question? Is something not clear about this? Since I spent so much time, I want it to be clear.
So it totally depends on the Riemann surface.
Totally depends on the
Remain surface.
Riemann circle. Who mentioned Riemann circle?
Most external remain surface may be happening. So right now,
Did I mention Riemann anywhere?
no, don't I'm asking.
Which is the Riemann circle?
Remain surface may come in finding point of the zone.
No, that's Riemann sphere. Yes, that is the Riemann sphere. So think of it as a complex coordinate. Riemann sphere is the complex plane with the point at infinity. All points towards the infinity identified as one single point. That's Riemann sphere. Riemann surface is the difference. Any other question? This is a 3D solid ball. Distinguish between the ball and the sphere. Sphere is only points on the boundary. X square plus y square plus z square equal to r square. Equal. A ball is x square plus y square plus z square less than equal to r square. That's a closed ball. X square plus y square plus z square less than r square is an open ball. So interior is the open ball. All points uniquely denote one rotation. On the surface, 2 points denote the same rotation. Any other clarification, question?
It means that their R is fixed and the whole ball R is not fixed. That is the plastic fixed. In 3D sphere,
Let's do it in 2D. 2D is easier to see. The disc, interior of the disc is a two-dimensional ball, open ball. If you include the boundary points also, that's a two-dimensional closed ball. Just the boundary points is a one-dimensional sphere. Is the boundary of the closed ball. In one dimension, this is an open ball without the boundary points. With the boundary points, this is a closed ball. Just the boundary points are 2 points. Just the boundary of the closed ball, that's just 2 points. Now in 3D, it's the interior of the ball. So everything inside is included. Boundary points not included, that's an open ball. Boundary points included, that's a closed ball. Just the boundary points is a two-dimensional sphere. The surface of the ball is two-dimensional sphere. So you can think of it as if you take a football, which is just the surface, that's a two-dimensional sphere. But if you take a, you get this ball for doing exercise or something, you have sponge or something, you have to press for exercise of your hand. All points are there. Material includes all the points inside. That's a ball. That's a real ball. Football is not a real ball, that's a two-dimensional sphere. From this point of view. Alright, any other question? Or a cricket ball. Cricket ball is also solid. It's solid, it's inside is included. What? Sweet. Yes. Unless there is a hole inside. Gulab Jamun has a hole. Alpha? नहीं अल्फा में टेक एनी वैल्यू फ्रॉम 0 to pi.
सर तो अल्फा मेजर करके पड़ता है.
अल्फा मेजर करते कैसे? Along the radial distance. Since you have not just the point of the surface, you have point of it inside, right? तो लड्डू के अंदर सब सारे points हैं ना. So how far inside the laddu you are?
सर ये डिस्टेंस हो गया सर ये तो डिस्टेंस हो गया सर एंगल का.
Distance और angle में फर्क क्या है? What is the difference between an angle and a distance? An angle is measured along a line. So I am measuring along a line, the radial line. And since I am not identifying, I don't have to worry about completing it or anything, right? Pi angle is not same as 0 angle.
Yes.
So I am only measuring from 0 to pi, that's a line, right? In any direction I can take a line. When I take line in any direction, I would have filled up the interior of the ball. Direction and angle are of course different. You are confusing many different things. This direction is given by these two angles. This is different from the amount of rotation. Suppose I want to rotate an object. I rotate about z axis. The direction is the z axis. Unit vector of the z direction. That's an independent quantity. Amount of rotation, how much I rotate by, that's another independent quantity. They are not related. What is your question? But that is for this vector. So angle तो निकाल दिया ना. What are its components? N is equal to cos theta sin phi sin theta sin cos phi and sin theta sin phi. What was the question?
जैसे वेक्टर्स में पूछता है कि डायरेक्शन निकालना है तो हम एंगल निकाल देते हैं तो यहाँ पे
डायरेक्शन उसने तो एंगल निकाल दिया है इसीलिए तो इसको थीटा फाई से लिखा है and its magnitude is 1 so I don't have to specify the magnitude I only have to specify the direction.
तो यहाँ पे रेडियस सर्कल है तो जो डायमीटर के केस होता तो डायमीटर 2 पाई जिस डायरेक्शन में तुम पॉइंट को ले रहे हो
I am not talking about vectors in three-dimensional space. I am talking about how to denote a rotation in three-dimensional space. So you take a vector, you rotate it. It will go to some other vector. X vector will go to x prime vector. I am not talking about these vectors. I am talking about the relation between this vector and this vector which is in this matrix. How to denote this matrix? What are the parameters in this matrix? There are three parameters, three angles, theta, phi and alpha. So I am talking about how to write this theta, phi and alpha in a geometrical space. It has nothing to do with these two vectors. Is that clear? Time is up. This 1 hour class was short and I missed one class yesterday. So I did almost nothing today. Well, not almost nothing, but I really seriously.
So on Tuesday we have only 2 classes. Can you take an extra class on Tuesday?
Tuesday I am taking an extra class already today. I have extended my class on Tuesday. Huh? If you request after Thursday after my class, if you can switch the 2 classes, then I can think of
ऑनलाइन पर
क्या फर्क पड़ेगा ऑनलाइन और ऑफलाइन कितना फर्क
से स्टार्ट
Sunday. Oh, sorry, the paper. Whoever is coming out.
क्या भाव वो मतलब फाइनल তাহলে তাহলে জেড অ্যাক্সিসটাকে আমরা এন্ডটাকে যদি সেম করে দিই তাহলে এক সপ্তাহই হয়ে যাবে মানে এখানে ডায়াগ্রামটা যদি এন অ্যাক্সিস এই ডায়াগ্রামটা বানালো তাহলে এক সপ্তাহ সেম হয়ে যাবে তাহলে কিন্তু একসাথে
Okay, so let us discuss DP or SP. Who are motivated from different sort of background motivations. This is the smallest non-trivial group that we have. I mean, non-trivial means until now we got cyclic, or if not cyclic, that we told that at T2 level or the fourth, it was still abelian. So for the first time, we have an example of a non-abelian group. We will see this. In the last class, we were a little sketchy about the description of this group, but we will see many things. This is like your I think an important example, you can learn a lot of ideas just by understanding this group. Okay? Everything else is more complex version of the thing. So, yeah. So for any group, let me focus on D3. D3 means by definition, symmetries of, it's a group of symmetries of equilateral triangles. And we don't want to be lazy or lousy about our conventions, so at least once we pay careful attention to what we do, and they should consistently be useful. There are different ways in which you can think about it, but let me just label the three corners as 1, 2, 3, so that eventually it will be easy for me to relate this with that. So remember, when I am talking about dihedral D3, I mean symmetries of equilateral triangle of a geometric shape. When I am talking about S3, I am not talking about any shape or anything. I am talking about permutations of three labels. Okay? So the context and the background motivation for the two groups to construct is different. But it so happens in this case, they are isomorphic. Okay? And we will go further. But for the moment, let us. This 1, 2, 3 that I have introduced are the labels of three corners. Okay? And so that eventually the operations that I think of as geometric operations of this triangle, I could have one way. This is not a unique way. I could have called this as 1, this as 2, this as 3. It could have maybe changed some correspondence, but it's the spirit of the correspondence that is more important. So this is for permutations, this is for geometric operations. Okay, so let us now define the geometric operations clearly. So, notations. So when I rotate this figure and I want it to come back to itself, the obvious rotation that I would have to make is R2 pi by 3. So what I mean by this is, you break this triangle, so let me write it here neatly. So by rotation R2 pi by 3, I mean an operation which starts with this this or whatever shape, and then rotates, and by definition this is counterclockwise. So I don't have to write it again and again, by angle 2 pi by 3 around axis pointing, passing through the center. So you can imagine something like this. Okay. So this operation is something like this. Get counterclockwise by this much angle around an axis passing through the centroid of this shape. So what is the resultant? One goes here, 3 goes here, 3 goes here. This goes here, that goes here, here. So 3, 2. Correct? 1. So this is the input, this is the output. Or this is the initial state or orientation. And let me continue to use triangle. So by writing them inside, I can imagine a cardboard with number 1, 2, 3 written. So they are simply moving with the cardboard. If I write them outside, I would imagine they are on the plane, on the blackboard, not on the card. Okay? So I want to consciously write it here. These are just the names or the labels of these corners. 1, 3. Okay, this is my operation. I have defined it. Okay? So whether you call them 1, 2, 3, you call them A, B, C, or by whatever other way you remember them, that is irrelevant. All I am saying is this is my operation R25, regardless of what I label them as. But I am deliberately labeling them as 1, 2, 3, not as A, B, C or alphabetic gamma, because it would be easier to then associate the corresponding or identify the corresponding permutation. Okay. So this is my R2 pi by 3 by definition, and if I were to find its correspondence with permutation, what happens? We could develop this convention, look at the initial reference position of the 3 corners. So the 3 corners 1, 2, 3 were like that. Now the label of the top corner becomes, so 1 becomes 2. Right? Because as far as the cardboard is concerned, it is the same cardboard, but somehow the labels have been exchanged. So 1 has become 2. This is what I mean by this symbol. 2 has become 3. And 3 has become, under this operation, 1. Okay? So you could remember like this: 1 has become 2, 2 has become 3, 3 has become 1, and this is back. So it's like a cyclic transaction. And this is what we said, this is a permutation, but in a more complex way you could write it like this: start from any reference point, 1 becomes 2, becomes 3, and 3 becomes 1, so you don't write it again, but that is, so this is your 3 cycle. Okay? So this is your permutation, 3 cycle permutation, an example of the 3 cycle permutation. And this is your rotation by 2 pi by 3 around the centroid of the shape in the counterclockwise manner. So this is a geometric operation, this is a permutation. And these permutations keep appearing in various places, but for the time being, let us keep it purely mathematical exercise. Okay, good. You define other operations. In the last class, if you remember, I just randomly chose this as 1, 2, 3. Right? Then this turned out to be 3 to 1, opposite. Okay, so just to make you feel happy or comfortable that I count